what. Ain't no mind in her. She only wants to play. But she's not for you. But she's not for you. I'm the only one who would let her act this way. But she's not for you. She's not for you. So she told you she found heaven in your eyes. Well, I think it's only fair to warn you that sometimes she lies, but it's your heart. I can't tell you what to do. She's not for you. She's not for you.
All right, this will be the fifth video in Unit 3. In Unit 3, we've been dealing with the respiratory system and respiratory hazards, respiratory diseases. We want to end this unit by taking a brief look at control strategies or control methods for inhalation hazards. How can we protect workers from the airborne contaminants in the workplace? This is just going to be a brief overview of those controls. In the second class, in the industrial hygiene cycle, we go into much more detail especially talking about ventilation systems. But as far as controls for inhalation hazards, one possibility would be to use safer materials, using some type of substitution strategy. Instead of using silica for sandblasting, maybe using walnut shells or some other materials that are sometimes used for blasting operations. Change the work procedures, change the tools, change the way the work is being done would be another option. Change the work procedures so that perhaps workers aren't in the vicinity of airborne hazards. Move the worker further away from the point source for the contaminants. Changing tools that would not cause disturbance of material, or less disturbance of material. Less airborne material that could harm the worker. But ventilation systems, this is the Cadillac of controls for inhalation hazards. And there are several different types of ventilation systems we can talk about. When I say that ventilation is the Cadillac of controls, it is the desired engineering control. When we can implement some type of engineering control or ventilation control that is going to provide the optimal protection for our workers. It's not always cheap, but safety is not always cheap. Sometimes it's an important investment. It's an expensive investment that we need to make in the health and safety of our workers, which would be a return on investment for our companies. There's local exhaust ventilation. I'm just going to briefly describe what we're talking about with local exhaust ventilation in this video. Dilution ventilation, also just briefly talk about that, and general ventilation also. Another option that for me falls under the heading of engineering controls would be different dust suppression strategies, using water to suppress the dust. If you're working with concrete, keeping that material wet so that when we're cutting it or breaking it or disturbing it in some other way, we're preventing that dust from becoming airborne. Then finally, we have respirators. As a last resort, we can use personal protective equipment. And I'll just briefly introduce some of the different respirator options that are available. Again, like I've said, part 2, we're going to hit this a lot harder. We're going to spend several units, several weeks, just talking about ventilation systems. We're going to get into ventilation calculations, ventilation system design, different design issues that can affect the efficiency of our ventilation system. But that's in Safety Management 4423, where we really dive in, dig in, hunker down, and study ventilation systems. But let's talk about ventilation systems just very generally, very broadly, very briefly. 3 types of ventilation systems: local exhaust ventilation, we're sucking out the bad stuff and we're replacing it with good stuff, with good air, good breathable air. Dilution ventilation, we're bringing clean air, uncontaminated air into the workspace to dilute the concentration of contaminants in the air. It works best with lower toxicity hazards and at lower concentrations. General ventilation, it's really useful for more than just controlling temperature and humidity, but that's often what we think of when we think of general ventilation. Temperature, humidity, also controlling nuisance odors in the work area. I'm going to go into each of these in a little more detail as we move through this lecture. Now, one note that I need to make, for some safety professionals, and you'll see this in some textbooks, they don't distinguish between dilution and general ventilation. They are lumped together. But for me personally, I like to make a distinction between them. Dilution ventilation, dealing more with higher level, higher toxicity contaminants. General ventilation, it's more non-critical types of contaminants and controlling that temperature and humidity and perhaps odors in the work area. And I do like to make that distinction, but some safety professionals do not. And that's fine. I don't know that one approach is really better than the other, as long as we understand our work environment and which ventilation system is best. We can call it whatever we want to, whether it's dilution or general or some variation or combination of the two. Now, complex ventilation systems, they're not going to be designed by safety professionals for the most part. We may be involved with that design. But complex ventilation systems, there are engineers with engineering degrees and engineering certifications, registered professional engineers who specialize in the design of ventilation systems. There are a lot of calculations involved, a lot of different variables to consider. Now, we will do some of the calculations that go along with ventilation design in the second industrial hygiene class, but not to the level that a ventilation engineer would go to when they're designing a system. But even though we're not designing the systems entirely, we need to understand as much as we can about ventilation design and different factors that affect the efficiency of our systems. A little bit more information about local exhaust ventilation. We're dealing with what we call point source contaminants. Contaminants generated from a specific operation, a specific location, like carbon monoxide coming out of the exhaust of a generator, silica dust that's coming off of a grinder or a saw. Flammable vapors from gasoline or other chemicals. As it evaporates, that's the point source. That liquid that's vaporizing, that's our point source. We're using local exhaust ventilation to suck it up at the source, at that point source. Zinc oxide fumes from welding. We have a system set up to capture those fumes immediately at their source. And when they're captured, they are removed from the work area. They are exhausted out into a safe area. There are other options besides just simply exhausting, but I'll save that for the next industrial hygiene class. But these are examples of point source contaminants, and there are many others, and you can probably imagine some yourself. But this is what we're talking about with local exhaust ventilation, removing the contaminants at the source. Efficient local exhaust ventilation systems, and that's the acronym LEV that's commonly associated with local exhaust ventilation systems, will result in what I call a clean atmosphere that is safe for workers. What's a clean atmosphere? Does that mean there aren't any contaminants? Well, for me, a clean atmosphere is when we have our focus contaminants, the toxins, below the action level. And normally that action level is going to be 1/2 of the Pell. Now, there may be standards that are more restrictive than below the action level. But for me, if I can bring my contaminants, my toxins, the bad stuff, down to 1/2 of the Pell limit, the permissible exposure limit, then I'm going to feel like we have successfully controlled that contaminant, that we've successfully exhausted that contaminant from the work area. Basic diagram showing the components of a local exhaust system. We have our stack or the exhaust. We have a fan that is moving the air through the system. We have perhaps an air treatment unit, a filtration unit, or other types of air treatment systems that's going to treat the contaminated air before it's exhausted. Not always necessary, but in some instances it is necessary to have some type of air treatment module built into our local exhaust ventilation system. Of course, our passageways, our duct system that the air is going to pass through, and that's going to connect all of our components. And then finally, the hood, the inlet, where the contaminants are captured at the source. So we have our hood, we have our ductwork, we have our air treatment system, we have our fan that gets the air moving, then we have our exhaust system. And again, a lot more goes into it than just these simple components. Fan efficiency is a consideration. And the hood design. Different types of hoods are going to be more efficient than other types of hoods or other types of inlets. And there's different types of hoods. But more on that in Safety Management 4423. Now here's an example of an industrial quality, industrial level local exhaust ventilation system. Now look at the size of the ductwork. And off of that main duct, that primary duct, you have several branches. Each branch is connected to a hood. This is a hot work process. It looks like it could be a galvanization process, maybe. And I'm not a general industry guy. I'm not exactly sure what's going on. But they're doing what appears to be some type of hot work process, manufacturing process. And as fumes are being created from that hot work, they're being sucked into the system through the hood, through the inlet, the branch duct to the main duct, and it's being exhausted to a safe location. There could be a treatment unit involved also, depending on circumstances, depending on location, depending on the toxicity of the contaminant. If it's a highly toxic contaminant that we're talking about, you can't just release it into the air. It's got to be treated before it can be released. or if the facility is located adjacent to a neighborhood. You don't want to release even low toxicity contaminants into a neighborhood where kids and families live. There's liability there. There's also the ethical side of that as well. But main point here, this is a glimpse of a local exhaust ventilation system like you might see in an industrial facility. Dilution ventilation. Like I've already said with dilution, we're blowing clean air into a contaminated space to lower the concentration of contaminants to a safe level. Or we could be, if we're dealing with flammable vapors, we could be lowering the concentration below the lower explosive level or the lower flammability limit. Or we could be using dilution ventilation simply to maintain adequate oxygen levels. We're bringing in fresh air to maintain adequate oxygen levels. Again, for me, the safe level best practice, like I mentioned before, is at the action level, 1/2 the OSHA, PEL, or below the lower explosive limit. This is most appropriate for lower toxicity contaminants that are found at lower concentration levels. If you have really toxic contaminants, or you have lower toxicity contaminants at high concentration levels, dilution ventilation may not be adequate. You may have to resort to the more effective local exhaust ventilation system that's going to remove those contaminants at their source. When you're using dilution ventilation, as far as the evaluation process or the monitoring process, you would certainly be testing your atmosphere prior to dilution to find out what the concentration level is. Then once the atmosphere is diluted, once the fresh air is brought into the system, you're going to monitor, test again to see if your dilution air has effectively lowered the concentration. And also, best practice, you're testing that atmosphere continually throughout the work operations to ensure that the system continues to function efficiently and continues to keep the concentrations at a safe level for workers. General ventilation. You can almost think of a general ventilation system as a heating, ventilation, air conditioning system like you might see in a home or a commercial building. The components are the same: ductwork, fans, heating, cooling, dehumidifying components perhaps, air cleaning components. Same principles. When you get into the engineering and the efficiency testing of ventilation systems, we're concerned about pressure in the system, the velocity of air movement, and the amount of air, the volume of air that's being moved through the system. Same thing with general ventilation. Same thing with the HVAC system in your homes. These are all of interest. Now, generally speaking, like I said before, the focus may be more on comfort, but may also be an important part of providing a healthy work environment. And let's not diminish the importance of the comfort of the worker. A comfortable worker is important to a company, I would argue. A comfortable worker that's not dripping sweat, a comfortable worker that's not working in a high humidity environment, they're going to be more productive. They're going to be more focused. A more focused worker, less likely to be injured, less likely to cause different types of problems for management. Employers should have as one of their goals not just the safety of the workers, but to some degree the comfort of the worker, because the end result is going to be better if the worker is comfortable. Again, these are some contaminants, some conditions that can be managed with more of what we would call a general ventilation system. Temperature, humidity, nuisance odors. We've talked about these three. Carbon dioxide and oxygen levels also need to be monitored and managed. Now here we are getting more into a higher level of a more serious safety concern when we're talking about oxygen levels. Same thing with tobacco smoke. There's hundreds of toxins in tobacco smoke, and I'm grateful that indoor smoking in public areas is pretty much a thing of the past. But at one time, you would go into a restaurant or an office, and half of the people are smoking, and the other half are being exposed to hundreds of toxins in the tobacco smoke. A general ventilation system properly designed could help decrease the health effects from the tobacco smoke. But there you might be getting into maybe local exhaust components as well. The local exhaust strategy, where you're removing as much of that smoke as possible and you're replacing the toxic smoke with cleaner air. Another concern that gets overlooked, and this goes along, really all of these go along with what we call indoor air quality, tobacco smoke, oxygen, carbon dioxide levels, but also off-gassing from building materials. A new building or a building that has been renovated with new materials, it can cause problems for the occupants because of the chemicals that are off-gassing from the new carpet, from the new countertop material, from the paint. There have been several instances where a new building has had to be thoroughly examined and studied because of workers complaining of illnesses, headaches, nausea, other health complaints, and it's been traced back to things like the chemicals in the flooring. Lumber liquidators, speaking of chemicals in the flooring, lumber liquidators a few years ago had to do a huge recall on some of their products because of harmful chemicals in some of the wood flooring they were selling. Now, filtration systems can help with some of these issues. Allergen control, biological contaminants, and nuisance particulates also can be a part of your general ventilation system. So a general ventilation system can have an important impact on the health of the worker, productivity of the worker, and so on. Back to the issue of indoor air quality, there are some OSHA publications that deal specifically with concerns about indoor air quality, and if anybody would like to read some of those materials, I'd be happy to share them with you. You can find them on the internet, different sources, but I have pretty much every OSHA technical manual and all the material from the EPA on indoor air quality. All I have to do is shoot you an email with those files attached. And that's a nice thing about OSHA and EPA materials. They are in the public domain. You're not stealing from anyone when you share those materials. As taxpayers, we all have a right to most of those materials, if not all of those materials. So we talked about ventilation. That's an engineering control. Another level of control that we hope we don't have to go to. If we have good ventilation, we may not need respirators. But if we're not able to control the airborne hazards with an engineering level control like ventilation or dust suppression, we may have to resort to using respirators. And there are so many different types and models of respirators. One of the most common would be a half mask respirator with changeable cartridges. They're changeable cartridges because you can use different cartridges depending on the specific toxins you're working with. We also have a full face version of this respirator. That's what we have here. This is a full face passive air purifying respirator. That's the technical term for what we have here. A passive air purifying respirator. It's passive because there's no pumps involved. It's air purifying because of these cartridges that filter the air as it enters the mask. It's full face because it covers the eyes, the nose, and the mouth. Now, the half mask respirators are also air purifying, but they only cover the nose and the mouth. They don't cover the eyes. A lot of times that half mask is going to be more than adequate, but if you're dealing with contaminants that can affect the eyes, then you want protection for the eyes as well. Or there may be contaminants that could cause harm to the skin of the face. That's another circumstance where the full face respirator would be required. We also have powered air purifying respirators. That's what we have in this picture. This does have a power unit with fans that are moving the air. Most of these are going to be positive pressure systems. They're pushing a positive air pressure into the mask. And there's also filtration components involved. They protect the worker in the same way, but again, they are powered, they are positive pressure systems. We also have what are referred to as atmosphere supplying respirators. A self-contained breathing apparatus is one example of an atmosphere supplying respirator. With an SCBA system, the worker is wearing a supply of air in tanks on their back. Usually on their back. It could also be there can also be tanks located out. Some escape respirators, it may be a small cylinder that they wear on their hip. But the full-fledged SCBAs, they have tanks on the back. And there's a lot of different variations of the SCBA respirators that we go into in 4423. Another type of air supplying or atmosphere supplying respirator is the airline system. And I have pictures of these on the next slide. I think I have pictures of both of these. But like I said before, if our engineering controls are removing the contaminants, or we're able to dilute the contaminants to a safe level, we may not need respirators. But even in those circumstances, depending on the toxins, respirators may be advised. Now here is an airline respirator. You have a compressor. And most of these airline respirators, they will have two connections, so you can connect two hoses. Two hoses means two workers. And this is a type of face piece that you'll often see with these airline respirators. This is a loose fitting hood that goes over the head. These are positive pressure systems, so they don't have to be tight fitting. That positive pressure flowing into the hood will keep all the bad stuff from coming in. But if you lose that pressure, then the bad stuff can come in because it's not a tight fitting face piece. Over here we have an SCBA, and they're wearing their air supply on their hip with a tight fitting face piece. Now this, depending on the capacity of the air supply, this may be classified as only being appropriate for emergency rescue or emergency escape use. If they only have 5 to 15 minutes of air, that's going to be an escape device. That, say you're inside of a coal mine and you hit a pocket of H2S gas. Well, you can put these escape respirators on and you'll have 5, 10, 15 minutes of air to get out of that area safely. Now here is an example. I didn't have one on the previous picture, but this is a half mask air purifying respirator, passive air purifying respirator. And here is another example of a powered air purifying respirator with the hose attached to a welding hood. One of the best discoveries ever made as a safety manager working with welders and bridge construction were these devices. The first ones I bought were $1,200, $1,500, relatively inexpensive, but it made our welders so much more productive that, as a safety guy, I'm more interested in their health. They liked it because it was more comfortable for them. In the summer, there was even a cooling effect. Even though these weren't air-conditioned units, the ones that I had, there was a cooling effect with that air, that positive pressure coming into their hood. And also, they didn't go home every night coughing and wheezing because of the fumes they were breathing through the workday. It was a win-win all the way around. We had an OSHA inspection on one of our sites, and the compliance officer raved on and on about how great it was to see a company that provided this equipment for their workers. But there are so many options out there. I'm just giving you a really quick and dirty overview of respirator protection devices that are available. 4423 will spend a full unit just on respirator types and some of the calculations that go along with it. A lot more calculations in the second industrial hygiene class. So something to look forward to. All right, that pretty much covers it for this unit. Just a quick summary of what I've talked about in this last video. There are a wide variety of controls available. The best controls are going to be at the engineering level, ventilation, or some type of dust suppression control. Administrative controls, which I really didn't talk about too much, but we've talked about before. A great example of an administrative control when it comes to these types of exposures would be worker rotation, job rotation. You limit the worker's exposure by rotating them in and out. Then finally, personal protective equipment, respirators, were discussed as it's the lowest level of control. It's the least desirable control. But in some work circumstances, some situations, that's going to be the best available control. There is no excuse for employers allowing workers to be exposed to respiratory hazards. We've been developing controls for many, many years. Manufacturers, engineers have come up with all of these wonderful control strategies and technologies. There's no excuse. Now, again, some companies will balk at the expense. As a safety manager, that's sometimes our hardest job, is to persuade our bosses, upper management, that spending money on these controls is a good investment for the company. And sometimes you have to be able to show them how it's going to be a good return on the investment, not just because of worker safety, but try to show them how it can increase productivity, how these controls can decrease turnover, how we can keep workers on the job and more productive for longer periods. If you can make those good arguments to management, you have a good chance of being successful in persuading them to invest in different types of controls, even the expensive types of controls. All right, that's it for me. It is late and I'm tired, so you guys have a good night, good morning. I don't know what time it is where you're at. It's late where I'm at, but I will see you in the next video. Let me know if you have any questions.